Welcome to the set theory primer. In this lecture, we look at the inclusion and exclusion principle and an application of it. Last time we looked at some basic operations on sets like the notion of union, intersection, difference, etc. We will need these notions, and let me not go into details of what they were. I am sure you know what these are. Here are some problems for practice. This one I've marked as star not because this is hard, but because I'm going to use it. It says that if we have a bunch of sets contained in a big set, then their complements, the intersection of their complement is the complement of their union. You can draw a picture and see why this is true, and also formal proof is not hard. All right. So let's look at the notion of cardinality. It is very simple. If A is a finite set, then the cardinality of A is the number of elements in A. So that's just a name. Basically, let's see an example. If A is 1, 2, 3, then the cardinality of A is 3. So this is the notation for cardinality. The cardinality is denoted either as NA or mod A, or some people use hash A, whichever notation you like. I like this. Okay, so it's a very simple concept and I don't want to stay on it. So here is a basic theorem that you must have seen earlier somewhere. So if A and B are finite sets, then the cardinality of the union is the sum of the cardinalities of the individual, but you subtract out the cardinality of the intersection. So if A and B were disjoint sets, then this one can easily see, of course, this is true. And even in general, you just make two circles, or maybe blobs. Oops. Okay, anyway, so this is A and that is B. This is the intersection. So when we write the cardinality of A, we count this guy. When we write the cardinality of B, we again count this guy. So we have counted it 2 times. And that is why we subtract off so that we do not overcount it. And you can write down a formal proof using induction, which I don't see the point doing. I'm sure you agree with it. All right. Here is a more general version, or rather the version for 3 sets. So again, we have 3 finite sets. And then the cardinality of the union is cardinality of the singletons, cardinality of the individual ones and then added. Then you subtract off the cardinality of intersection of 2 of them, and then you add back the cardinality of the intersection of all of them. Again, you should see this using a picture, but let me give a proof. The proof is as follows. Let X equals A union B. Then cardinality of X union C, which is same as that, we know from the previous slide, is equal to cardinality X plus cardinality C minus this thing, which is equal to this, which again by the previous slide is equal to so far what happened, this is equal to that by the previous, this is same as that. And now for this, I did not mark the exercise as star, but what I'm going to use is that. So I'll spell it out, but let me write it. So here I have used the fact that basically A union B intersection C is equal to A intersection C union B intersection C. Again, you can prove it formally, but draw a diagram and you'll be convinced. So we have this much, and now let us just rearrange these folks to club them together. And here again, we will use this formula of cardinality of union. So finally, this is cardinality A, cardinality B, cardinality C minus A intersection C cardinality plus B intersection C cardinality minus the cardinality of the intersection of these two folks, but that is A intersection B intersection C. So ultimately it is what you were trying to prove. Yeah, so basically it's an inductive argument. Once you know the answer for two, union of two things, you just club two of the things together and then apply the previous one and play around a little bit, and that's it. So the general version is the following. Suppose we have n finite sets, n is any positive integer, then the cardinality of the union of all of them is, first you sum the cardinalities of the individual ones, then you sum the cardinalities of all the pairwise intersections. So there are n choose 2 intersections that you can form, and you sum up the cardinalities of all of them, but with a minus sign. And then now with a plus sign, so the signs alternate. This was a plus, minus, dot, dot, dot. This time you will be summing up the cardinalities of intersections of 3 of these. So you get n choose 3 here. And this will go like that. And again, if you want to formally prove it, you can just use induction on n. That is one way to establish this. Later, in a different primer, maybe in a primer on functions, we will look at a different proof. A very nice, clean proof of it. But for now, you can just prove it using induction. Okay, now let us see an application of this. This is called the inclusion-exclusion principle, or at least a version of inclusion-exclusion. So I will refer to it as such. It's a powerful theorem and very useful. So here is a very famous problem. Suppose we have 5 envelopes and 5 letters, and the envelopes as well as the letters are marked with numbers from 1 to 5. So the letter 1 belongs in the first envelope, 2 in the second one, and so on. And here is, I'm sure you know that if suppose we were tasked with placing these envelopes, placing these letters inside these envelopes in a manner that one letter goes only in one envelope, so no envelope contains more than one letter, and every letter reaches at least one envelope, so it's a 1-to-1 correspondence. Then how many ways are there? Disregarding the numbers, then there are 5 factorial ways, because there are 5 positions that you have to deal with and 5 objects that you want to arrange in a sequence. But suppose we had some other constraint. So here is the constraint. We want to put every letter in an envelope, so every letter goes inside somewhere. No letter is hanging free. Each envelope gets a letter, so no envelope is hungry. So that is the same as saying that, you have a 1-to-1 correspondence here. But the third condition is an interesting one. No letter goes into the matching envelope. So we want 1 not to go here, 2 not to go here, 3 not to go here, 4 not to come here, and 5 not to come here. So this is called a derangement of letters. We have deranged. We want to count how many derangements are there, how many ways are there to completely mess up the correct placement. So it's a non-trivial problem. It's not clear what should be the answer. But we will look at it using the lens of the inclusion and exclusion principle, and it will just fall out algorithmically. So here is how we do it. So let X be the set of all possible, assignments of letters to envelopes satisfying condition 1 and 2. So as of now, we have excluded condition 3. So this X is basically all possible ways to have a 1-to-1 correspondence between the letters and the envelopes. We are only satisfying the first 2 conditions. So that means the size of X is 5 factorial, so that we know. This is 5 factorial. And let A1 be all... Again, let me copy this. A1 is what? A1 is all possible assignments of letters to envelopes satisfying condition 1 and 2, and such that letter 1 goes into envelope 1. So in other words, A1 is all possible one-to-one correspondences where the first letter reaches the correct envelope. And similarly, we can define it for each I. So instead of just A1, let me write a J here. Letter J goes to envelope J. So this is defined for J from 1 to 5. All right, and what do we want? So first of all, each of these are subsets of X, of course. And what we are looking for is the following. We are looking for A1 complement. We want the letter 1 not to go in the correct envelope, meaning letter 1 not to go into the envelope labeled 1. At the same time, we do not want the second letter to go into envelope 2 and up to all of these. So we want to count the cardinality of this set, and once you realize this, the problem is almost solved. So this is the main observation. This is why we were defining everything. So now let us just focus on computing this. So yeah. Wait a second. Is this? No, this is not vertical. Yeah. So by the star mark problem, this is same as the complement of the union, which is same as the size of X minus the size of the union, right? This is a subset of X. So the size of the complement is the size of X minus the size of whatever. So I hope that is clear. And now here we can use our inclusion and exclusion. So this union is equal to this minus that. Yeah, there are 5 terms. Let me write them in 5 lines. Minus that minus, going to get fishy very soon. Sorry, this was a plus. Now a minus. We do not really need to write everything, but I'm being very, very fastidious. And then a plus. So this is actually just the intersection of all of them. Okay. What about this guy? So I hope you realize that the cardinality of each AI is the same. It's going to be 4 factorial, because what is A1? A1 is all the one-to-one correspondences where the first letter goes into the first envelope. So the remaining 4 envelopes can arrange themselves in 4 factorial ways. So this is 5 times 4 factorial. The first term is 5 times 4 factorial. Similarly, the second term, let's just count cardinality of A1 intersection A2. So if the first and second go in the correct places, the remaining 3 can arrange themselves in 3 factorial ways. And there are 5 choose 2 such pairs. So this is 5 choose 2 times 3 factorial, which is 10 times 3 factorial. This is similarly 5 choose 3 times 2 factorial, which is 10 times 2 factorial. This is 5 choose 4 times 1, which is 5. And this is equal to 1. Because if each letter goes into the correct envelope, there's only one way to do it. So what is finally the cardinality of the unions of this? This is equal to 5 times 4 factorial, which is, I don't know what is the best way to count this. So that's 120 minus 10 times 6, that is 60, plus 10 times 2 is 20, minus 5 plus 1, This is equal to 80 minus 5 plus 1. So 76, I suppose. Yeah, that is 76. And therefore, the cardinality of the required thing, this is equal to cardinality of x, which is 5 factorial, minus 76, which is 120 minus 76, which is 44. So there are 44 ways to derange the 5 letters. And that's a non-trivial conclusion. Yeah, so it's a beautiful proof. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.